Hey everybody, welcome back to another lecture video. In this chapter we are going to be looking at aldehydes and ketones. We'll look at how to name them, we'll look at how to identify them, we'll look at some of their characteristic reactions. This includes reacting them with alcohols to form something called hemiacetals and acetals, as well as oxidation of aldehydes to form carboxylic acids, and we'll look at how we can reduce these ketones and aldehydes into alcohols. And so that's kind of the predominant themes of this chapter, though we will look at some physical properties and some neat rearrangements that some of these ketones do. So let's start with just talking about their structure. So the functional group of an aldehyde is called the carbonyl group. And the carbonyl is that C double bond O. Now these R and R prime here can be other atoms. Now in methanal, actually the simplest of our aldehydes, or we call it formaldehyde also, the carbonyl group is actually bonded to two hydrogens. So both of the R groups in my sort of little example here would both be hydrogens. Now in other aldehydes, it's only bonded to one hydrogen and to one other carbon group. So if we were to put an H here and leave R as some other carbon group, whether that's just a CH3, like in ethanal, or a CCH3, so meaning two carbons essentially. Oh wait, no, not this guy. No, I was getting at this guy. So C double bond O with an H and then CH2, CH3. So two carbon groups, or so on and so on and so on, as long as one of those carbon groups remains a hydrogen. Now, the functional group of a ketone, so these first two here are aldehydes, and this one over here is a ketone. A functional group of a ketone still contains the carbonyl carbon, but in this case, both of the R groups are going to be carbons. If we were to take a carbon that's double bonded to an O, add an H to it, and then put, let's say, an OH on it, this would still be I think this would still be an aldehyde. Be a weird, actually this would not be an aldehyde. This would be the simplest carboxylic acid. This is the carboxylic acid functional group. So there's not many other things that we can attach in that R position other than carbon for it to stay a ketone or an aldehyde. And most of the functional groups that we'll look at are actually going to be replacing, that atom with different other atoms. So we've got ketones, we've got aldehydes. Now, we need to learn how to name these. So to name an aldehyde, we basically change the E ending of the parent name. For example, so this would be 1, 2, 3, 4, 5 carbons. So instead of pentane, right, we're going to lose the E on pentane and we're going to add Al. So it'd be pentanal. Pentanal. All of our aldehydes are going to end that way. Because the carbonyl group of an aldehyde can only be at the end of a parent chain, like if we can't put the C double bond O anywhere else, if we put it here, it's no longer an aldehyde. Now it's a ketone because the two things attached to that carbonyl carbon are both carbons. One of them has to be a hydrogen for it to be an aldehyde. So since they can only go at the end, the numbering will always start with that carbon as the number 1. So there's no need to put a number in front of a name. Like one pentanal. It can only be one pentanal, so we don't need to say that. Now, for unsaturated aldehydes, we do indicate the presence of the carbon-carbon double bond by changing the ending of the parent alkane from -ane to -ene. So, for example, if we were to have, if we were to have, let's say, this guy, right? This is no longer 1, 2, 3, 4 butane, it's butene. Right? So instead of this being butene, or in this case 1, 2, 3 butene, it would be 3-butanal. So here it still gets the al ending because it's an aldehyde, but we would have changed butanal to butenal if there's a presence of a double bond. So enals are for double bond containing aldehydes, and anals or butanals would be for regular alkanes, saturated alkanes. And of course 3 here would be the position of the double bond. The IUPAC system does retain common names for some aldehydes, including these 3. So for example, this guy right here would be trans because of the fact that this double bond right here, this double bond has something on one side and then on the other side of the double bond. They're not on the same side, right? So that's what trans is. Trans 3-phenyl 2-propenal, or we call it cinnamaldehyde. Cinnamaldehyde, yeah. It's what you essentially get the cinnamon flavor from. We have benzaldehyde, though I'm not sure how that's much different from the common, what the IUPAC name would be. I guess we would call it phenaldehyde? Phenylaldehyde? So benzaldehyde is from almonds, though I'm not really sure why that's common. Vanillin, that's a common name, vanillin. Here's the structure of vanillin. This, you don't really see the aldehydeness in here, but this CHO is the aldehyde. So we would have the O, and then there'd be an H. And I'm drawing it like this because there would be 120-degree bond angles here. COH, represented as CHO often. COOH will be for carboxylic acids when we get there, I think in the next chapter. So there is some common names that are used. Now for ketones, the parent alkane is still the longest chain that contains the carbonyl group. We indicate the presence of the carbonyl group by changing the ane of an alkane to -one. So the ANE ending becomes an ONE ending for the ketone. We number the parent chain from the direction that gives the carbonyl carbon the smallest number, just like we would any other substituent when we're naming alkanes. And then the IUPAC system does retain the common name for acetone, even though we could call it 2-propanone. So acetone is one of those common names that everybody keeps. But if we were naming this, we would go 1, 2, 3. So this is propane becoming we're changing the E from the ane to -one. So it's just the E becoming the -one. Because we don't say, for example, butane, we don't say butone. We say butanone, butanone. So it's not the ANE, but the E, sorry. So this would be propanone, and it's 2-propanone because the carbonyl is happening on the 2. In this example, we number to get to the carbonyl on the shortest amount of spaces. So if we go this way as opposed to this way, we get there with it being the number 3. So 1, 2, 3, 4, 5, 6 carbons would be hexane or hexanone. It's 3 because that's where the one is, the ketone. And then this one also has a substituent. And even if it had 2 substituents, let's say, there was something else on the 6, like a chloro or something, we would say something like 6 chloro, 5 methyl, 3 hexanone. So even if there was more than one substituent, nothing changes from how we were naming them previously. Cyclic ketones, same way. This would be cyclohexane. So because it's a ketone, it's cyclohexanone. Now for ring structures, the carbonyl carbon will automatically be the number 1, so we don't need to say 1 cyclohexanone. In this case, it does have a substituent on it also, and this substituent is a methyl. So here, that's why it has the 2, and it's not 2-methyl 1-cyclohexanone. The 1 is implied by just the fact that the ketone is part of the ring. Now, to actually name an aldehyde or ketone that also contains something like an OH or an NH2, a hydroxyl or an amino group, I could write that. We would number the parent chain to give the carbonyl carbon the lowest number still. We would indicate that the OH substituent is called a hydroxy. So this would be, 3-hydroxy 4-methyl, because it's on the 3, the hydroxy, the methyl's on the number 4. It's a pentanal, so we don't have to say anything about where the position of the carbonyl is. But we would call the OH hydroxy here. In this case, we've got hexane or hexanone. This is a ketone, so we do need to say that the ketone is on the number 2, because it could be on the 3 or the 4 or the 5. Well, I guess the 2 or the 3, because if it was on the 4 or the 5, we would just number that 2 or the 3, but from the other side. But it does have places that it could be, and so we need to specify. So it is 2-hexanone with a 4-ethyl and a 3-amino. So amino and hydroxy are how we would name these amines or these alcohols, right, when they have a ketone or an aldehyde functional group in them. To that effect, if we wanted to name this as an amine, then we would have to call the carbonyl group a keto group. Okay. There are some common names that get derived from the carboxylic acid that the aldehydes come from. Ketones don't become carboxylic acids, but aldehydes do. And so typically if we have a carboxylic acid, we get this common name for an aldehyde by dropping the word acid and changing the ic or the oic part of the acid to aldehyde. So for example, acetic acid, we would get rid of the word acid, and then acetic, we would lose that part and just say acetaldehyde. Acet, and then say aldehyde. And that's because this is going to reduce to that. In the presence of hydrogen gas and a catalyst, we can reduce the carboxylic acid into an aldehyde. Now, we could name each alkyl or aryl group bonded to a carbonyl carbon as a separate word, followed by the word ketone, kind of how we were doing for ethers, or how we could do a little bit with amines, how we could just say, triethylamine or methyl ethyl propyl amine. We can do the same thing with ketones. So for example, in this case, on the carbonyl carbon, we've got a methyl group and an ethyl group. So we can say in alphabetical order, it should be ethyl methyl ketone. So yeah, this is a typo. Ethyl methyl ketone. Though if you said methyl ethyl ketone, somebody would still draw the same thing. But you're just saying the groups and then saying ketone. Second example here, we've got an isopropyl, which is just a propyl connected at the second carbon. And then we've got an ethyl as well. So this is just ethyl isopropyl ketone. So it's a neat little way that we can just kind of shorten ketone names. Let's see if you guys could name this guy. So this is propyl. Actually, it's phenyl propyl ketone. It's not a benzyl, even though it's a benzene. Benzyl has a CH2 on it before it would connect. There's an extra little piece that goes with benzyl. This is phenyl propyl ketone. But again, that's kind of how we would use the common name. We'll come back to naming some aldehydes from carboxylic acids when we get to that chapter. So a carbonyl bond is polar. You can see it here. The oxygen bond, the oxygen will have a partial negative charge on it, and the carbon will bear a partial positive charge. So, and we've seen some polarity before. So aldehydes and ketones are polar molecules, just like alcohols and amines tend to be. So as polar molecules, these guys are going to have higher boiling points, higher melting points than typical alkanes, and they will have slight more solubility, but that will depend really on how large the molecule is. So you can, again, see here in red, more electron density than down here. So we can designate that with separation of charge, which is what polar is. In liquid, aldehydes and ketones, so kind of aldehydes here, ketones here. No, I lie. These are all aldehydes. This is all formaldehyde. The simplest aldehyde, right? Just one carbon with two hydrogens on it. There's actually weak intermolecular attractions between these partial positives and the partial negatives on the neighboring molecules. Though there's no hydrogen bonding possible, because there's no H's connected to O's like we saw in alcohols, these do still have higher boiling points than their normal alkanes. But they have lower boiling points than alcohols and carboxylic acids, compounds in which there is hydrogen bonding possible. So I have a table here that you can see some of these. We can compare some of these. So these are 6 compounds that have roughly the same kind of molecular weights, but we can see how their functional group essentially changes their boiling point. So the lowest here is this diethyl ether. So, right, diethyl ether. That has a slightly lower boiling point, which is odd, than pentane. You would think that the oxygen there would somehow make it have a higher boiling point, but not the case. Though it could be because it only has 4 carbons compared to 5 carbons. Butanal, so then butanal with its aldehyde, right? So and its polar group, suddenly it jumps from 36 to 76. 2-butanone, same number of carbons as butanal, but the carbonyl being more in the center of the molecule actually makes it closer to 80. And then you can see butanol, the alcohol, and the carboxylic acid. So butanol doesn't even really matter which butanol. There's just one of them, one butanol, and then propanoic acid. So polar and hydrogen bonding, polar and hydrogen bonding. So you can see why maybe this would be more, have a higher boiling point than this. And then the fact that this has hydrogen bonding with OH on it, you can see why these guys don't have as high a boiling points. Now, in regards to these two molecules, with the carbonyl connected to, let's say, two carbons, and a carbonyl connected to, let's say, even one hydrogen, we want to see which one of these is going to be more polar. And if we think about this being polar, and this being negative, and this being positive, and this being the case as well, and then we try to see which one of these is actually more polar, we can look at what the carbon is connected to. So this carbon here is connected to an oxygen that's pulling its electrons. So that carbon has two choices. It can just let its electrons go, which it clearly does because it ends up positive, but it can also try to pull electrons from neighboring atoms to try to compensate. In both of these directions, it's attached to other carbons that have the same electronegativity as itself. So this carbon and its neighbors, they're all the same in the way that they pull on electrons. So this carbon doesn't really get any electron density from these two red bonds here. No electrons kind of move this way to compensate. So this is polar. Now, on the other hand, we've got this carbon over here in the aldehyde, and while it does have a bond to a carbon, it has a bond to a hydrogen, and a hydrogen actually has a different electronegativity than carbon. It's lower. So this carbon is able to get a little bit of electron density from this hydrogen, meaning that some of those negative electrons come and lower the overall positive charge here. So whatever the polarity of this bond, this one is slightly less polar because the carbon was able to get some of those electrons back from that hydrogen. Now that's going to create a slight polarity here as well, but we see a difference in the boiling points just due to that carbonyl carbon. The aldehyde carbonyl is not as polar, and so it doesn't have as high a boiling point or a melting point as a ketone does. Let's talk about oxidation. So aldehydes are oxidized into carboxylic acids. So here I've got hexanal. And carboxylic acids can be created by various oxidizing agents. One of those is this potassium dichromate that I'm showing you. Here there's an acid catalyst. But essentially the carbonyl carbon is going to be oxidized. So that means it's going to gain bonds to O or lose bonds to H's. And in this case, it's already got two bonds to that oxygen, so it can't gain any more bonds to it. So it has to lose an H. And we're going to replace it with a OH. So our hexanoic acid, we're not naming them yet, but is just the carboxylic acid version of hexanal. Liquid aldehydes are so sensitive to oxidation, actually, by just oxygen in the air, that they actually have to be protected from contact with the air during storage. If you have benzaldehyde, which is that oil of cinnamon, and you expose it to air, it quickly and very easily oxidizes into benzoic acid, which loses all that cinnamon smell and taste. Ketones resist oxidation by most oxidizing agents, including potassium dichromate and molecular oxygen. So we don't see ketones reacting. To form, let's call it an oxidized product. What was it? Potassium dichromate is K2Cr2O7 with sulfuric acid, right? So we actually have a neat test we can use. We use Tollens reagent. It's a specific reagent for the oxidation of aldehydes. This one in particular will deposit a silver coating on the inside of the container. So if you use glass container, it makes a nice little like silver mirror on the inside. But we can use Tollens reagent to actually identify if we have a ketone or an aldehyde. Let's say that we have a product and we don't know what it is. If it reacts with a Tollens reagent, then it's an aldehyde. If it didn't react, then it was a ketone. We also have a Benedict's test that we can use. This one uses copper ions that are normally blue, and in the presence of an oxidized aldehyde, they'll turn red. We can use this actually in the medical industry to detect glucose in urine. They're able to use Benedict's test because it'll oxidize certain sugars. These are usually the aldehydes like glucose and fructose. Okay, so oxidation of ketones is resisted. So again, this is an aldehyde that's undergoing carboxylation here, or turning into a carboxylic acid. Now, reduction does happen. So the carbonyl group of an aldehyde or ketone can be reduced to an alcohol group by hydrogen in the presence of a catalyst like we've looked at before. The reduction of an aldehyde results in a primary alcohol. Remember, the aldehyde functional group, the carbonyl is the edge carbon. It's the one on the end. So that means automatically it's going to become a primary alcohol. The ketone, on the other hand, is never on the end, right? If the carbonyl was on the end, it'd be an aldehyde. So these always turn back into secondary alcohols. Secondary alcohol, primary alcohol. Again, and all we're doing here is we're adding hydrogens to both sides of the double bond. So a hydrogen adds here, and a hydrogen adds here, right? That's why this carbon now has two hydrogens instead of the one that it already had, and the oxygen now has a hydrogen. Same thing here. It's going to gain a hydrogen, it's going to gain a hydrogen. Now, the most common laboratory reagent for the reduction of an aldehyde or ketone is called sodium borohydride. This reagent contains a hydrogen in the form of a hydride ion, H-. So this one acts like like an anion. It has 2 electrons and a negative charge. Now, in this hydride ion, the hydrogen has the 2 valence electrons, and in the reduction of sodium borohydrate, the hydride ion adds to the partially positive carbonyl carbon, which leaves a negative charge on the carbonyl oxygen. So you can see that here. It attacks the sort of the nucleus or the nucleophile, positive charge, forms a bond. So now carbon kicks its electrons out from that double bond up onto the oxygen, which now bears 3 lone pairs where it only had 1 before, and that gives it a negative charge. Now then the reaction of this intermediate with an aqueous acid will give the alcohol. So whether or not that's water or some kind of acid catalyst, there will be a proton being donated. Essentially, those lone pairs will reach out and grab a hydrogen from something. So then that gives us our alcohol. Now we can see from this second reaction, or this reaction down on the bottom here, that sodium borohydrate doesn't affect carbon-carbon double bonds or aromatic rings. So that's what I'm showing you here. So in cinnamaldehyde, adding sodium borohydrate does not reduce the benzene ring. It also does not reduce the alkene, but it specifically goes after, right, the carbonyl carbon. So this is a really neat reducing agent to use on these aldehydes and ketones when we want to protect the double bond, the alkene. In biological systems, the agent for the reduction of aldehydes and ketones is actually the reduced form of nicotinamide adenine dinucleotide, and we call that NADH. If you get into the metabolism, we're going to get into metabolism later in the semester, but NADH is a reducing agent. It is good at donating hydrogens to other molecules that are going to be oxidized. Now, this reducing agent, like sodium borohydrate, delivers the hydride ion to the carbonyl carbon of an aldehyde or ketone. So again, it's going to be in that form, and it's going to add to that guy. And then the reduction, so in this example, you can see the reduction of pyruvate, which is the end product of glycolysis, actually gives lactate. So in the presence of, if we don't have oxygen around and we can't take pyruvate into our citric acid cycle, which is an oxidative cycle, we need to regenerate NAD+, so that we can get some energy. And so then this reaction becomes very important. And this happens in your muscles, actually, when you start to work out too much and you don't have a good oxygen flow, is that pyruvate, which is the breakdown product of glucose, starts to get converted into lactate, which then becomes lactic acid in your muscles. But that is so that we can get NADH to turn back into NAD+, so that it can keep, making more pyruvate and using up glucose. We'll get there. Let's talk about the addition of alcohols. The addition of a molecule of alcohol to the carbonyl group of an aldehyde or ketone forms something that we call a hemiacetal. Now, or a half acetal, and I'll show you what an acetal looks like also. The functional group of a hemiacetal is a carbon that's bonded to one hydroxyl group and one alkoxy group. So essentially, it needs to be a carbon that has an OH on it and a carbon that has an O something else on it, OC something. So OR is a good abbreviation. It just has to have an R where that's more carbons, some branch of carbons. That's a hemiacetal. So these happen from aldehydes and ketones. Aldehydes and ketones will react. Remember, there's a lone pair of electrons here on these molecules. In fact, let's see, I don't think I have a reaction to show you specifically, but we get an attack here. We get a bond shifting up, and then we get rearrangement of a hydrogen. This hydrogen will come over here. And so you can see that that's going to have the effect of attaching that group, and then the oxygen doesn't want to have too many bonds, and so this H shifts over and gets added here. And so we've turned a ketone or an aldehyde into an alcohol and what is kind of like an ether group. That's a hemiacetal. Now, hemiacetals are generally unstable and are only minor components of an equilibrium mixture, except in one very important type of molecule. When a hydroxyl group is part of the same molecule that contains the carbonyl group, and a, let's say, 5 or 6 carbon-membered ring can kind of form. So we have sugar molecules that do this. Lots of our sugars have OHs on them, and then they also have an aldehyde or a ketone group. This leads to the hemiacetal cyclic form. So some kind of alcohol can actually come in here and add to this bond. They connect together, and then we get a rearrangement that we looked at before, where the O of the carbonyl sort of gains the hydrogen from the O group that was coming in. And so then here you see it. There's the carbon attached to an OH and then to an OR, right? The rest of this stuff here is the R that's on that O. So this is a cyclic hemiacetal, and this is exactly what happens when our sugars form. We get stuff like this. So here we have a carbon attached to an OH, attached to an O other stuff, O everything else. So this is a hemiacetal, and it's what glucose is and fructose is, or not fructose, galactose, when they are in their ring form. And then when we add two sugars together, we're going to see the acetal formation. So let's take a look at what happens. So all I'm saying there is that when you bring in another alcohol and react another alcohol with a hemiacetal, you get an acetal. So let's say it this way. Ketone or aldehyde, right, plus alcohol equals hemiacetal plus alcohol equals acetal. So we can add 2 rounds of alcohols to these types of molecules. So a hemiacetal will react further with an alcohol to form an acetal plus water. There's a dehydration synthesis here, so a water molecule is ultimately lost in the connecting of these 2 new molecules. The functional group of the acetal is a carbon bonded to 2 OR groups. So here you can see the original acetal that we have. Here's the carbon with the OH and the OR. It's being added to another alcohol, right? Another OH. And here they're color-coded so you can see what's actually changing. The OH is going to be replaced with the O everything else. So then we end up with a carbon attached to OR, and then also attached to OR, 2 different, well in this case they're the same. They're both ethoxys, ethanes with an oxygen on them. But they're color-coded so you can see how they belong to the different molecules. And then we lose the OH from the hemiacetal, and we lose the H from the alcohol. So this OH and H add together to make a water. So we will always get a water at the end of these acetal formations. Sorry, just acetal formations. All steps in these hemiacetal and acetal formations are reversible. And as with any other equilibrium, we can drive them in either direction by using Le Chatelier's principle. So if we want to drive this to the right, we use a large excess of alcohol, or we remove the water as it forms from the equilibrium mixture, and this just keeps making more. If we wanted to drive it to the left, if we want this reaction to go this way actually, then we just use a really large excess of water. And a lot of water with an acetal will break that back down into hemiacetal and ethanol. Lastly, let's talk about one of the concepts, rearrangement concepts that happens with ketones. And this happens with fructose, which is a ketone, and it ultimately leads to fructose turning into glucose in our bodies, and so that's why we can metabolize fructose and glucose pretty much evenly. A carbon that's adjacent to a carbonyl group is called an alpha carbon. So in this carbonyl group right here, we have 2 alpha carbons. We got this one and this one, right? I don't know why I'm drawing more pen marks on the already arrows. So, and the hydrogen atom bonded to it is called an alpha hydrogen. So this has a couple alpha hydrogens, 5 alpha hydrogens, and 2 alpha carbons. So what happens is an aldehyde or ketone that has a hydrogen on an alpha carbon is actually in equilibrium with a constitutional isomer called an enol. The enol comes from the fact that it has a alkene in it, right, and an alcohol in it. So this is an enol. And the enol form, which contains the alcohol and the double bond, exists in equilibrium with the acetone, with the ketone or the aldehyde form. And again, they go back and forth. The ketol, the keto form is usually the one that predominates. Aldehydes don't really often have hydrogens on alpha carbons, so usually this is a ketone thing, hence the name ketoenol, but it does happen occasionally with the right kind of aldehyde. And so when you are predicting which way it'll go, you can actually we can actually draw it. So let's see. Let's draw the structures for the 2 enol forms that form for each ketone. So there's 2 forms for each ketone. So again, the double bond here is going to end up moving to one of the alpha carbon hydrogens, and then we're going to get an alcohol and a alkene. So just as a reminder, we've got 2 hydrogens here on that guy and 1 hydrogen here on that guy. And so the 2 forms that we can get, one of them would be if the double bond formed to the left. We would get that guy. And also if the double bond formed to the right. If it went this way. And that hydrogen that was there ended up on the OH. So these guys would all be in equilibrium with each other. For the bottom one, so we have 2 directions as well. This guy has 3 hydrogens on it, and this one has 2 hydrogens on it. So these 2 alpha carbons both contain alpha hydrogens. We could get that guy, and we could get the double bond forming the other way. When the double bond forms this way, we actually could get 2 versions of this. I drew the cis version, but we could also get the, trans version, where these groups are on opposite sides of the double bond. Here they're on the same side of the double bond. But again, this one in particular could give us 2 different forms. We don't have to draw them both out, but cis and trans isomers are possible for that enol. So that's keto-enol tautomerism, and the end of the chapter. So for these, just practice the naming, like always, and it's just, if you've been practicing the naming, then it's subtle changes, just ending changes. Some common names that actually makes them easier. Know their physical properties of the aldehydes and ketones. Draw some reactions. In fact, here's a good one that you should practice. It's something like, if you have, I think I saw it in your book. Maybe actually, yeah, it's like you have this ketone, and they're saying draw the reagents that you would need to get it to turn into that. And then what would you need to get it to be that? And then how could you turn it into, these variations? BR, and then this one would just be saturated. And so they'd be like, just in general, ketone into the alcohol, that's a reduction. So you would need some kind of, either hydrogen gas, like you could do here, right? Or like we learned, sodium borohydrate. Or what about the alcohol into the alkene? Well, we know that that's a dehydration reaction, right? I think acid catalyzed dehydration. You have to look that up. How to get the alkene into the to the dibromo? I believe that was when we were adding halogenations, right? This top one, hydrohalogenation, right? So this is a good way to kind of practice your reactions, or draw some aldehydes and then think about what alcohols they would be, they would become, or draw some ketones and think about, what alcohol this would be, or what alcohol could you draw that would oxidize to give you this ketone. Those kind of brain puzzle type, brain flexing type problems are going to help you in this class, though you're not going to be drawing too many things on the exams. But definitely try naming and drawing. 4-hydroxy 4-methyl-2-pentanone. Try to draw it. That'll be good practice. And then as far as keto enol tautomerism, just be able to do like what I just showed you here, or if I showed you in the previous problem, just know how those two forms are related. If I ask you a true-false question where I have this ketone and I say, is this alcohol in keto enol tautomerism equilibrium with this one, you should be able to answer that. You should be able to know where the alpha carbons are and what that means, what an alpha hydrogen is, and so on. All right, guys. Then I look forward to your questions. Keep using the discussion board. Email me if you have many questions. And I'll see you in the next video. Take care, guys.